Alright, welcome back everyone to section 3, the definite integral. Here we have three main goals for this part. We'd like to first discover how the definite integral accounts for when the function dips below the x-axis. We've only dealt with cases when it's above the x-axis so far. The second, we would like to use our calculators to actually calculate out the exact value of the definite integral. This is very nice. Great use for our calculators. And then number 3, understand why calculating area under a curve actually is useful, right? It has real-world applications. It's more than just a way for mathematicians to, torture students and things like that. So, yeah, it actually has some good applications. So we'll get into that. So let's start with number 1 here. We have this nice function, couple negative signs here, which means it's probably going to be below this x-axis, and I'd like to calculate out the right-hand sum on the interval from 0 to 6 using n equals 3. Let me use our calculator here to start graphing this thing for us. So I actually did this a little bit. So negative 7 times 2 to the negative x, and then if you go ahead and you stare at a graph, this is what it looks like. And so you can see, I've portioned out just a piece of that for us to actually sketch. And for our purposes, right, it's really nice to use a table to get some of these values. So the first one is at 0, it outputs negative 7, and then negative 3.5, and so on and so forth. So let me get out my blue pen. So at 0, it outputs negative 7, 1, 2, 3, 4, 5, 6, 7. And then at 1, it outputs negative 3.5, 1, 2, 3.5. And then after that, I think it was 1.75. Oops, not that one. Negative 1.75, and then negative 8.75. So let's see, negative 1.75, then negative 8.75. That's about all I can remember here. Then negative 4.3. So a little bit less than a half, then negative 0.2 something. And this is getting very close to 0, but on the negative side. It never quite makes it there, right? So that's up to 6. I actually sketched 7 as well. So yeah, very close to 0, but on the negative side. Okay, so if I was to sketch this function, again, it would look something like this. I would connect all the points. Nice curvy line here. There we go. So you can see that this is all below the x-axis. I'm interested on the interval from 0 to 6. So here is 0, 1, 2, 3, 4, 5, 6. This is where I stop. So I'm interested in maybe this area right here to some extent. And I would like to approximate this using my right-hand sum. So actually, let's erase this because I'm going to want to use that for rectangles here. So, and I want n equals 3. N equals 3. So if I was to break this up into 3 even pieces, right? So again, here is my B, here is my A, my n equals 3. So this would be B, 6, minus A, 0, over 3. That's saying that each piece should be length 2, if you want 3 pieces. So again, 2, 4, 6, and you can see I have 1 piece, 2 piece, 3 pieces, right? Okay, so use the right-hand sum. So we can see, first of all of our widths here are 2, all of our delta x values, the widths of these rectangles. We're using a right-hand sum, so for each one of these pieces, I'm going to use the right interval. So I'm going to use this one for the first, something like this. Right-hand sum, so this one for the second, and then again very, very close to 0, just a little bit negative here. So those are going to be my heights of rectangles. And so when I go ahead and plug these in to try to figure out the values for these heights, right, so let's first of all maybe plug in when x equals 2. When x equals 2, as we saw, our value was negative 1.75. So the height of this thing should be negative 1.75. So according to this, the right-hand sum should be equal to delta x, so that's 2, the width of the rectangle, times the height of the rectangle, which is negative 1.75, plus delta x times, and then the next rectangle, again we're using the right-hand sum, so on the right-hand endpoint, and so this is at 4, right? 0, 1, 2, 3, 4. I want the function's height at 4. And so the function's height at 4 is negative 0.4375. Negative 0.4375. Added a little bit of a dot there. Plus 2 times, and here at 6, again using the right-hand endpoint, right Riemann sum. There we go, negative 0.1094, negative 0.1094. And so let's see, I can go ahead and calculate this. And I think you can already see what's happening here. I'll emphasize this in 1 second. So 2 times negative 1.75 plus 2 times negative 0.4375 plus 2 times negative 0.1094. Enter. Negative 4.59 and change. I'll say negative 4.59. And there is my final answer. And of course, this is getting the area of these 3 rectangles, and the claim is that it approximates the area under the curve. This one, ooh, that's going to be bad. Too thick, but okay, you get the idea. So the answer is, right, that this is something to do with net area. So, right, normally area can't be negative, but actually here we're getting out a negative number, negative 4.59. So the key word, back when we brought up definite integrals, was actually the word net area. So let me go way back up here, too far. Right here it was the net area between f of x and the x-axis. And so I didn't really emphasize that until now, and that means, right, net area means that it actually can be negative. And so the claim is when f of x is above the x-axis, the area is counted positively. And then when the area is below the x-axis, the area is counted, when the function f of x is, oh no, typo, below, I'll fix this in your guys's, below the x-axis, the area is counted negatively. Negatively. So below the x-axis means that it's counted negatively. That's the big thing. And that's our first thing that I wanted to bring up for you guys. What happens when a function dips below the x-axis? Well, it's counted negatively. Okay. The second big idea, which we actually already brought up in the first video, I kind of spoiled the surprise here, but if you want your left Riemann sum, or your left-hand sum, and your right Riemann sum, or your right-hand sum, to be more accurate, use more rectangles. So more rectangles makes the sum, I guess with an S and everything, makes the sum more accurate. And so again, this is the link to this Desmos calculator here, and let me bring it up really quick. All right, and here it is. In fact, let me zoom out a little bit more. I've changed the function on us this time, so I have the function x squared minus 1, and you can actually see it has at some point where it's counted negatively, right, where it's below the x-axis, so I have that in red, and then sometimes where the area is counted positively, right, it's above the x-axis. And so, you know, you can change these a's and these b values. I have from -1 to 3 right now, and the claim is, in this case, that if you increase the number of rectangles, that this area is better approximated. So here we are at n equals 3. Right now we're using right-hand sums. Of course, if we want left-hand sums, there you go. Just switch it over to the left. Right, back and forth. So left and right-hand sums. Okay, so let's take a look at this thing. If I increase the number of rectangles, I'm going to go from 3 to 10. So here's from 3 to 10. You can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. And this looks a little bit better. It looks better than we had it at 3, right? And then if you increase it even more, I'm going to actually use the dragger here. Let's increase it to 20, right? The claim is this is looking even better, right? Still an approximation, but even better. If I increase this to 50, let's say, or a little bit under that, now it's looking very good, right? In fact, now it looks so good that it's hard to see that it's actually off, and I'll zoom in a little bit to see, okay, yeah, it is actually still a little bit off, but it's looking very, very close. And let's increase this all the way up to, I have 100 max right now, so here is 100. right? But actually the power behind Desmos as well is that you can actually switch this. So let me do from 1 to 10,000. I don't know, that might break it. So we're at 100. Let's do at 6,300 rectangles. Again, this looks very, very smooth. You can't even tell that it's off at all. If I zoom in, still I can't tell. Still I can't tell. When can I first even tell that there are rectangles? Ah, here we are. You can actually see that it does have rectangles, that it's off by a little bit. But the claim is that we are doing a really, really good job of approximating this area under the curve by using lots and lots of rectangles. You can think of this as we want our rectangles to go to essentially infinity, right? As many rectangles as we possibly can. Okay, so with this in mind, right, let me pop over to our notes again. The claim is that if you want to do a really, really great job, right, with this definite integral and actually get equality, then you would want your number of rectangles to go to infinity. So this theorem right here says that you want the limit as n goes to infinity, right? So this is your number of rectangles. And then the claim is it really doesn't matter between the left-hand sum and the right-hand sum so much. So I'm going to use maybe a right-hand sum. So remember the right-hand sum was the right-hand endpoint, height, times the width of the rectangle, plus maybe on the second interval, right, the right-hand endpoint, x sub 2 times the width of the rectangle. And this went on for a while, dot, 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 plus, again, and we stopped at f of x sub n, right, the endpoint of the last subinterval times the width of that rectangle. And so if that n right there was to go to infinity, you were adding up essentially infinitely many areas of rectangles, and that these would actually become equal to one another, and that this is the area under the curve. And the claim is this is, we can do this by hand. It's a bit of a pain, but this is one thing that our calculators really, really excel at. So I would like to show you how to do this with our calculators. So let me go ahead and pull out our calculator here. Remember that I already have this graphed. So if I go into the graph bit, there it is. And the claim is that if I go to calc, right, so I'm going to do second trace and get to calc, and there's an option down here, right, number 7. And if I go ahead and choose number 7 here, it's going to ask for a bunch of things. So the first thing is, where would you like to start integrating, right? What is your lower limit? What is your a value? So in this case, the answer is 0. Enter. What is the upper limit, right? When would you like to stop integrating? And our claim is, right, we are interested from 0 to 6. So I'm going to do 6. Enter. And then it does a really good job. It shades in this area and everything, and it says that our actual integral is equal to negative 9.941 blah, 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 right? So negative 9.941 blah, 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 right? And so this is what our definite integral is equal to, and the claim is the calculator does exactly what I brought up here. It uses areas of lots and lots of rectangles in order to calculate this out. And now you can actually see here maybe how far we were off, right? Back here we said that the area was around negative 4.59. This is pretty far off, right? But it's because that we used we only used 3 rectangles, right? There was all this area left over that we didn't take into consideration, and we probably should have, right? There's a lot missing here. So negative 9.941 is the actual area under this curve. Notice it's negative because it's below the x-axis, and our calculators can do this for us. So this is really nice. One thing that is a little bit of a pain is that your calculator does need to be able to see the function. Like if you do it with this method, your calculator actually needs to be able to see this function. So for instance, if I was to do, let's see, let's go back to my calculate button, and let's say I wanted to do our integral 7 here, and let's say I wanted to do from 0 to 100, right? So add up all that area from 0 to 100, enter, and it says, oh, error, right? Because it wants to be able to actually see that function, and our window is only set from -10 to 10. So there's actually a little bit better of way to do this that where you don't have to mess with the window of the calculator and all that stuff. So let me show you that really quick. And so let's go back to the home page, and I'd like to go under math, right? So under math? Ah, there we go. For some reason I must have had the second on. So yeah, under math, if we go down a little bit, I don't know why there we go. fn int. fn int, again, is the integral. It's a definite integral. And so let me show you how to use this. So fn int, and then I'm going to go ahead and plug in our function here. So -7 times 2 raised to the parentheses -x close parentheses. And then it asks, what are you integrating with respect to? So we do a comma, and then you do x. So this is like the dx part. And then you do another comma, and then you input, where do you start? 0. And where do you stop? In this case, let's do the 6th one, right? And then I do close parentheses and enter. And there we are, the same number that we had before. -9.941, blah, 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 blah. Okay, but now the power behind this one, like I mentioned, is that if I bring up that same entry before, I can plug in 100, I can plug in whatever I want into this format, right? And actually, it doesn't need to be able to see the graph in order to be able to actually give you the answer. So let me hit enter. This one will take a little bit longer. And the answer should be around, yes, -10.09 and change, right? So therefore, this is a nicer method because you don't have to mess with the window on your calculator. So this fn int is also a very powerful thing. Okay, that's all I want to talk about for the calculators here. Let's bring up applications, right? Like I promised, this is the third topic, is that this actually has a real world meaning, right? So consider this velocity function here, v of t. T is in seconds, v of t is in meters per second. I would like to calculate out the definite integral from 0 to 5 of v of t dt and ask what are the units, try to interpret my answer, right? So this function right here looks awfully geometric, right? So I'm not going to try to get an equation or anything like this. I'm going to use the fact that it looks geometric. Okay, so let's go ahead and see here. I have, this is 0, 1, 2, 3, 4, 5. So I do care about this entire picture right here. On this first part, right, you can see that this is going to be a triangle. So it has height 2 and width 1. But because it's below the x-axis, remember I'm going to count it negatively. So let me go ahead and start up the integral from 0 to 5 of our v of t, which I don't know an equation for, but that's okay, is going to be equal to 1/2 base. So the base is 1. And then if you'd like to, you can say the height here of this triangle is -2. Or you can say that it's 2, but it's counted negatively because it's below the t-axis, or the x-axis, right? So somehow you need to make sure that this number right here is negative. Okay, let's do the next piece. So here is another triangle. It has width 1 and height 2. So this is going to be 1/2 base times height. So the height is +2. Notice it's above the t-axis, or the independent axis. So it does need to be counted positively. Okay, the next one. The next thing right here, this is a rectangle. Width 1, height 2. So this is going to be just width times height, 1 times 2. After that, kind of running out of colors here, I'll use blue, I guess. So again, a rectangle here. Oh, not a rectangle, a triangle. Again, height 2, base 1. So this is going to be 1/2 base times height. Again, it's above the x-axis, so it's counted positively. And then finally, I'll use pink. Another triangle, but it's below the x-axis. We have base 1, height -1 if you'd like, or you can just remember it's below the x-axis, so it needs to be counted negatively. So 1/2 base times height. And so all together, let's see, this simplifies down 1/2 and the -2 kind of cancel out a little bit. I get -1 plus 1 for the green one, plus 2 for the orange, plus 1 for the blue, and then minus 1/2 for the pink, right? And those are all the pieces. And so if I was to calculate this out, let's see, we have 3 minus 1/2, so that's going to be 2.5. Okay, but this again is a velocity, right? It has some real world application to it. So let me start thinking about units, right? So it says, what are the units? So if I was to go back to this purple one really quick, notice that the t-axis, right, which is corresponding to this width here, this has units of seconds. So if you wanted to say this is 1 second, right? And likewise, this -2, this height right here, well, this is on the y-axis, which is mapping v of t. V of t has units meters per second, right? So this -2 is -2 meters per second. And so if you were to multiply these two things together, right, the seconds and the per second, right, because this division, would cancel out. And the units that would be left over are just meters. And the claim is this happens for every single one. Let me do one more. Let's do the green one. Again, the width of this rectangle, this has something to do with the horizontal axis, the t-axis. This is 1, and t has units of seconds, so this is 1 second. And again, the 2, the height, right, this is a y value, mapping something with v of t. This has units of meters per second. So this is meters per second, right? And so again, if you were multiplying these things together, the seconds would cancel out and your units would be meters. So technically, all of these things, this is -1 meters, and this is 1 meters, and so on and so forth. 2 meters, 1 meter, -1/2 meters. And so when you add a bunch of meters together, the units here are meters. So there is our final answer, including the units. And so the question becomes, try to interpret our answer, right? Try to figure out, what does this mean? I mean, it means 2.5 meters. Well, you had a bunch of velocities, right? So you can imagine someplace I'm starting at time equals 0, and then it looks like I run backwards, right? I run in the negative direction, I have a negative velocity, and then eventually I come to a stop, right? My velocity is 0, and then my velocity becomes positive. I'm running in the forward direction. Running in the forward direction, my velocity is 2 meters per second, and then I bring it back down and I stop, and then I run in the negative direction a little bit, right? And so the claim is this 2.5 meters is the distance from where you started. This started, and this is at t equals 0, right? Because I started at t equals 0. In this case, I ended at t equals 5. Distance from where you started at t equals 0. If you're in some physics class and stuff like this, again, the distance from where you started, this has a nice physics term. This is called displacement. How much were you displaced from where you were originally? Okay, so the big thing here, the big interpretation of why we want area under a curve anyway, is because if we have f is some rate of change function, of a quantity, so let's say capital F. So in this case, our function was a rate of change of distance, right? Meters per second. It was telling you how much the meters were changing, right? So if some other bigger function, capital F, that is that velocity, right? So our little f is the derivative of some bigger function, in this case, distance or position, really. Then the integral, the definite integral from a to b of f of x dx is the exact total change of f. In our case, it was distance, right? The total change of distance, which we're calling displacement sometimes, from x equals a to x equals b. All right, so this actually tells us how this bigger function, capital F, is changing. So let's see that it's not just velocities, actually. It's any old rate of change. So let me show you another example here. We have a pump is delivering water into a tank. It has a certain rate. So in this case, it's liters per minute. So you can think this bigger function is how many liters do we have in this tank, right? T is time in minutes. Since the pump is turned on, how much water has been pumped in the first 3 minutes. So in order to solve this question, notice it doesn't even have an integral sign anywhere in this. It's just words. And you have to decide that these words mean, right, you want to add up how many liters are being pumped each minute to get the total amount of liters that you need to do area under the curve, that you need to integrate from 0 to 3, right? It's the first 3 minutes. So from time equals 0 to time equals 3 of this r of t function, dt. Right? Because we're going to be integrating with respect to time in this case. So the integral from 0 to 3, definite integral, 6t squared plus 20 dt. And again, we're going to get the actual answer here using our calculators. So I'm going to bring out our calculators again. And I'm going to use this fint, so math, all the way down. Should just remember the number of this thing, 9, I guess. Can plug that in next time. Fint, and we have 6 times, and remember we're going to switch these t's to x's because that's what our calculator understands. So 6 times x squared plus 20, we are going to integrate with respect to x, so comma x, comma from 0 to 3, close parentheses, enter, and we get the answer 114. So the answer here is 114. But again, this is a real world problem. Before, the units were liters per minute. Time was in minutes. So when you integrate this, remember this is telling you, back up here, the total change. The total change in the amount of liters. So in this case, the claim is that there were 114 liters added from where you started, right? Notice I could have already had 20 liters or something in the tank to begin with, or I could have had 50 liters or something like this. This is just telling me how much it changed. What is the total change in the amount of liters that were in this tank? And the answer again, right, 114. That's how much it changed. That's how much was pumped in during the first 3 minutes. All right, that is the end of this video. I will see you guys in class.